Well, welcome everybody, and thank you for taking the time. And today, we are very happy to have Dr. Trung Le to give us a seminar. And I'll just quickly introduce Dr. Lee, and then we'll let him have the time for the talk. And then after that, we'll take some questions. So Dr. Lee is an assistant professor at the Department of Civil Construction and Environmental Engineering at North Dakota State University in the US. And he's recipients of several awards, including one from the American Physical Society and a fellowship from the US National Academies. And he actually did his bachelor's in Vietnam. In the university name, if I didn't say it wrong, it's Tui Doi University. He got a master's degree at the Asian Institute of Technology in Thailand, and then his PhD was at the University of Minnesota. So he's always done a lot of fundamental phenomena investigations in biofluids, and in particular trying to study vorticity dynamics and structures, and fluid structure interactions. So we're quite pleased to have him here because what he does is really kind of within the core interest of some of us here at Imperial College too, and so it's definitely a pleasure to host him. So Trung, it's over to you.
Yeah. Thank you very much, Dr. Yap. And it's my pleasure and my honor to have an opportunity to share my research with you. And so I think, it is a great chance. So I'm going to go ahead and then I'm going to share my screen. So the talk today is about cardiovascular flow. And as Dr. Yap mentions, I share a lot of the common interest with his research. And I hope that this talk will um, be useful for other researcher in the department and also students who are who would see some example and then pursue the research in future. And here, of course, I need to thanks a lot of sponsor, NDSU, North Dakota State University, National Science Foundation, and others who support my research. And I also would like to thank my collaborator over the years from different institutions and different departments across the United States and other countries who supported and provided me the data because I do mostly simulation, and so I really need the support from people who do experiment, and that's why their support is critical for my success. So today we'll talk about cardiovascular flow, and I would like to start with this picture. And for some of you who are not familiar with this picture, is from Leonardo da Vinci, and probably you're familiar with this Da Vinci Code, and then it's actually one of his code is into the right hand side is you can see this, the left one is easy to see, right? This is a heart, human heart, and on the right hand side you would see some sort of drawing, and for who are for people who are not familiar with this is called vortex ring in the aortic valve, and we'll go back to this phenomenon later, but it's very interesting because a few hundred years ago, this person has a vision of how blood flow looked like in human heart, which is amazing, right? Without any sort of device or any sort of uh, just barely using some observation, he can infer blood flow pattern in a very, very accurate way, and we will see next in the next about 20 minutes. So, what are the what are the things that we want to talk today? So first of all, I would talk about the cardiovascular flows. So in the blood flow in the heart, and blood flow in the brain. So that's two main parts that I'm going to focus on. And in particular, I would talk about blood flow inside the human heart and specifically in the left ventricle, and that is the project that we've been working on for about 15 years. So this is the picture in the middle part, for this department. So I don't have to talk much about the cardiovascular system, but specifically the picture in the center is the human heart from a donor at the University of Minnesota, which is close by. It's about 200 miles from here. Well, actually, we just crossed the street to Minnesota. So this is a heart from a donor that, for some of you who are not familiar with the anatomy of the heart, this is the left side of the heart where blood flow comes from the lung through this atrium, and then the left atrium, and then from left atrium it go through the left ventricle. And you see the structure, which I show the number 1, 2, 3, 4, 5 here. They are the structure of the valve, the mitral valve, and these 5 is the location where the aortic valve. You cannot see it clearly, but we'll go back to that. That is the aortic valve. And so this type of structure ensure that blood flow going into one direction from the lung through the heart and through the other part of the body. And we'll spend a lot of time discussing that today. And then I will mention a little bit about the current project that we're working on, which is the role of blood flow and fluid flow in and blood cell, specifically how it interact with sort of cancer cell. That is our current project. So the story is it started for a long time ago, so 40 years ago, where this is for some of you who are not familiar with this, where people grow this endothelial cell, which is the cell that line our arteries, in a petri dish. There's no flow, and the cell looks very irregular. However, when they apply the flow, the cell respond immediately. And if you can see the black arrow here, the cell actually aligns very well to the flow direction. However, and that is the flow is laminar, which is the condition that dominates in our body. Okay, so laminar flow is the flow that is basically very, very smooth, very, very slow. But when the flow becomes turbulent, which is the flow become chaotic, then the cell respond in a very unexpected way. It grow into irregular development of cell morphology. And so that's the observation, ignite a whole bunch of line of research. And that's why this is basically the start of this cardiovascular flow research. So that is the sort of motivation for the flow and cell interaction. So time passed, and currently we have the technology to acquire very good data. For example, on the left is the MRI, magnetic resonance imaging data from Dr. Yoganathan from Georgia Tech, which show the exact anatomy of the heart, left heart, I would say, left ventricle and the aorta. But more recently, we are not just only we are able to capture the anatomical geometry, but also we are able to capture blood flow inside left ventricle, right? So it's on the right side is the 40 flow MRI, which is the modality that you are able to capture the three-dimensional blood flow inside the left ventricle. And it was 7 years ago, and now 40 flow MRI become even more and more popular in research, and hopefully in one day is going to be coming to be used in clinical practice. And that is the talk that we will mention today. And so what is the goal here? Well, the goal here is to understand, as an engineer, my goal is to develop numerical methods so that it can replicate the blood flow inside left ventricle. And you see that the vortex ring that I mentioned earlier in the first slide of Da Vinci will show up repeatedly in the cardiovascular flow in different applications. And here on this left ventricle, you see that this vortex ring will show up in the left ventricle like this. And it would appear, then this method that I will mention will be applied for the prosthetic valve, and specifically bilevet mechanical heart valve. And that is the goal, to develop these method that can simulate mechanical problem in cardiovascular flow. So This problem obviously complicated, right? Because it's, blood is a complex fluid, and the anatomy of the heart, in particular, and others part of the human body are very complicated. I mean, it's not just a simple sphere or cylinder, but it's really complex, and it's moving, right? The heart beats, it moves, and so this problem is challenging, and so we need to develop a specific code to be able to handle those things. And so what we do, well, first of all, we take these patient MRI data from hospital, and we reconstruct the motion of these heart, and then we can acquire additional modality from, for example, ultrasound or others. We can have sort of, blood additional information about blood flow dynamics and tissue property, and then we reconstruct the motion and then perform CFD, and we got the data result like this. So, by the way, this framework was invented probably 15 years ago, and now I think many groups, including Dr. Yap group here at the Imperial, using pretty much the same framework. So this is not something that is is uncommon. It's very common for many researchers to use the same framework. So now for us, as the mechanics, kind of people who do computational mechanics, we want to actually go into detail to solve this kind of problem. And so I'll briefly describe what we do with our method. I'll not go into detail because people who have different background would not be, but we'll just describe what we will do. So the method we developed is called sharp interface immersed boundary method, which is here, which I highlight in red. There are many methods that can be applied for this problem, cardiovascular flow problem, and in the literature you can see a lot of them. But we think that this sharp interface immersed boundary method is appropriate because for this kind of problem, because it can handle complex geometry efficiently, and that's what we use that. So what is the main idea? Well, the main idea is that instead of solving the equation for complex geometry, which is challenging because the computational mesh would have to deform, we simply represent the body of the object. In this case, I demonstrate by the prosthetic valve. So let's say bileaflet mechanical heart valve or Charlie-Bled valve. I just show as an example. In the background mesh, which is in black, we solve the equation of the flow. We'll go back to that, but typically it is, if it's a big artery, you can consider the blood flow as the incompressible Newtonian fluid. We solve those equations there, and then we can solve the dynamic equation for the structure part. In this case, the leaflet, and the leaflet are represented by triangular mesh, blue one like this. So you can actually decouple the equation of the structure from the fluid domain, and we can solve different kind of structure from thick body like bileaflet mechanical heart valve, or thin body like tissue valve. So that's we will show next. And so what the main idea is the following. You have an object which is in red. So I separate this red part here. The body is in blue, and instead of solving exactly the body, we remove the body out, and we supply the equation with the boundary conditions. So we call immersed boundary conditions, which in the cyan color here. These are the nodes that we supply the boundary condition there. And by doing so, we can actually be able to simulate the motion of the body very efficiently. So you actually don't have to remesh. You don't have to make the mesh topology change with time. We can just track the motion of the object, and then we supply the boundary condition there, and we solve the equation. Because of this way, we can actually simulate highly deformable object, and therefore the code is highly efficient. We can do it thick body, we can do it thin body. In thin body, like a tissue valve, we'll see next. Then you have a little trick. You have a trick to separate the upper part of the tissue and then the lower part of the tissue. So you have to handle that a little bit. And we use high performance computing. So we use different technique to handle that. And in here we use hybrid stacker non-stacker scheme, which is solving this solving issue with the pressure on one side and the other side, and handle the so we have capability to multi-block, which helps for these complex anatomy. And for the structural part, we can solve the thin body, and we can also handle very good coupling between the fluid and structure by directly at Neumann partitioning. Basically, we solve the equation as we see below. So when we say coupling scheme, we mean we solve the fluid equation. So here we call directly at Neumann partitioning. So you have first you solve the fluid domain, and then from you get the pressure and the velocity from the fluid domain, which is the fluid flow. You calculate the loading, from this pressure and velocity from the loading, and then you use that as the boundary condition for the structure. So you can have the motion of the leaflet from the force of the fluid. And we do it many, many times. We call fixed point iteration. So we solve fluid and structure many, many times. So until we get fully converged result, and that is the main idea. So that's sort of what we do to get the solution. And if you have any question, just interrupt me, or you can have question after we the talk. Okay, so now after we develop this method, the first part is to ensure that the code or the method works. It should basically be able to simulate the physical phenomena. And as I mentioned earlier, in the first slide, right, we are curious about Da Vinci work, where he showed that this vortex ring appear in the heart. And a vortex ring is not something that is new. Vortex ring has been studied, especially in England, since the 1900s. So it's like more than 100 years of experience, both from the physical side and the engineering side. We know that when let's say you have a cylinder, a piston cylinder, if you displace a column of fluid, this cylinder from cylinder to the ambient fluid, the shear layer, I would call, in mechanical engineering, is shear layer, that it transfers momentum from the fluid, and here you can see the roll up. This nice roll up, like a donut shape, will appear at the end of this nozzle, and that is called vortex ring, because all of this momentum will be transferred to this vortex ring, and that vortex ring propagate along this axis. And in nature, actually, you can see this vortex ring in many, many places. For example, this dolphin, right? This dolphin, they can blow air. They can blow air through their mouth, and those, nice ring will form as the impact of this, this transfer of momentum. And so the point is that whenever you see a pulse, you will see this ring form. So you send a pulse, you see a ring, and that's exactly what they see in 2011 by Michael Marco. He showed a very clear example of this ring formation inside a human heart in the left ventricle. Now Michael Marco is at Northwestern, and so now we want to basically replicate this process using our code, and that would be the next step. But first, we want to choose a case where we can replicate it in a control case, and that case is in a very classical vortex rings formulation. So we have a piston cylinder here, you have a cylinder here, and the fluid is injected from the piston move, and then it would eject the fluid and create a vortex ring. And what you are seeing here is called vorticity. So vorticity basically is the curve of velocity. So in fluid mechanics, is a way to identify this vortex ring. And experimental data here from Dr. Longmire from University of Minnesota, and she did 2 experiments from 1998, and which is what is called particle imaging velocimetry. So if you're not familiar with this, it is a technique that you can actually to measure the flow field. And she showed that, very interestingly, if you have a flat cylinder, then you have a classical vortex ring, so symmetric, like a donut shape. However, if you have an inclined nozzle, so if you chop this cylinder one side, it's like a 45-degree angle, then the ring is not symmetric anymore. One side of it becomes bigger, the other side becomes smaller. And it becomes even weirder if when she did another experiment where she's able to develop this volumetric measurement V3V system from PSI. PSI is a company here in Minnesota, and they are able to capture this, three-dimensional structure of this ring. So it actually doesn't look like a ring. The first ring is a ring that you typically see, right? It's a circular one, it's a nice one, which is number 1, but it has additional structure, which is number 2. You have 2 legs, 2 and 3, they are connected to the ring. And so this is very, very interesting, and they don't know why a simple perturbation of the exit can make this ring transform into a complex structure. And so we do the simulation again to explain that. And so we do this simulation here. So we have this nozzle, we cut it like exactly as experiment. We prescribe the piston motion exactly as experiment. And what we found is that we actually see a similar good agreement between these PIV experimental data and our simulation. On the left side is the experiment. So you can see the big core on the left, and we, on the right column is our simulation. And you can see that the big core, we capture very well from the CFD and the experimental result. And so they agree well. However, simulation has the ability to look into the nozzle, because PIV experimental data cannot look inside the cylinder because some restriction of optical access, so it cannot be done. But CFD, you can see that. And interestingly, what we found is that because of this stopping of the piston, the entrainment of the fluid, so the fluid outside actually enter the cylinder and create this entrant called 2 here. So you can see that this number 2 here actually is the additional core that occur inside the cylinder. That is different. Now, from some simulation result, now we reconstruct the process. The first, we found that this ring number 1, which is nice, very, very nice ring form, and that's very clear from the simulation. Later, this ring become bigger and incline, right? So that is some exactly experiment. But when the piston stop, the entrainment of the fluid outside create an additional ring, which is ring number 2. And these 2 rings, R1 and R2, they are connected together by a thin shear layer. And by the way, what we're looking at here is the contour of vorticity magnitude. So you can see clearly that these 2 rings are connected by a thin shear layer. As time passed by, this shear layer evolved into the leg, right? That's what you see in this delta structure here. So you have this, delta, and it connected to the main ring and second ring, and it becomes this delta shape, which agree very well with this V3V measurement of Longmire in 2010. So now we have a story, right? A simple perturbation of the exit will lead to the formation of this complex ring or complex Vortex structures here. So basically what we want to demonstrate is that our code can replicate this ring, complex ring, in a very accurate way. Now, interestingly, additionally, we see this behavior. So we see this twisting mode. In the first ring, we see this twisting mode. So we look back at the literature and another experiment from different group, from Dr. Lim from National University of Singapore in 98. He observed this twisting mode in this ring, and we also observed that in our simulation, and we are now we were very excited that we can even capture this tiny detail of twisting mode. So going back, okay, now we have this. We are able to capture this ring in the in the lab in a very well-defined setting. Can we actually capture this ring in the heart? Okay, so what we do is that we say, okay, now in literature. So why we need to do that? Well, because now we are able to capture flow dynamics inside a left ventricle, as I mentioned, in the beginning of the talk. And actually, there is a lot of work in the last 10 years, especially in the work of 4D flow MRI and 4D ultrasound, trying to quantify the signature of the flow, right? So, for example, here, people show that in pathological condition, especially when you implanted the valve, the flow inside the left ventricle actually change. And what they want to do is actually quantify this change and correlate with these pathological condition, and somehow we'll use that signature for early diagnosis and treatment, monitoring and treatment of the patient, and that is the main purpose. So you can replicate this. Hopefully, you can figure out a marker, some sort of biomarker, to monitor the disease progression. So what we do is that, okay, so now we take these data from the patient, we reconstruct this motion of the left ventricle, we apply the appropriate biorecondition, and so we found that the ring indeed appears inside the left ventricle, and this ring is a little bit, its behavior is a little bit special. So first of all, when it formed, it's sort of sort of symmetrical, but as it propagate along this left ventricle axis, it deformed and it's not just circular anymore, but it stretched into along one line and become like an elliptic shape. It's not a circle anymore, and that is actually observed in the 40 flow measurement. They also observe that, and here is the 40 flow MRI data from Elsbad. Elsbad is is also my college that he's at Northwestern, and so on the left side is the contour of lambda 2, which is similar to is the way to visualize this vortex ring inside the heart, and you can see this ring, right? You can see this ring from the mitral orifice that form here. Now, again, 40 flow because is limited by the time frame. For example, here the entire cardiac cycle is captured only in 30 frame, because you have physiological constraint of the patient, and so you cannot it's very challenging. It's very challenging to increase the frame rate. So it would be better if you could replicate this process using high resolution for simulation. And so that's what we do. So here we want to show on the left side is the 40 flow MRI measurement, and on the right side is the CFD simulation. And so from the CFD, you can see that the ring, while from the 40 flow, the ring is observed to form and dissipate, and then in the CFD, you can observe more structure because we can see the ring actually. We can actually resolve the ring better. So here is some sort of still shot to show the comparison between the 40 flow and the CFD result. Okay, so now we are able to we are kind of convinced that we are able to replicate this ring in real patient specific anatomy. So how about the prosthetic valve, the valve, heart valve basically, and probably if some of you are not familiar with this, so heart valve is why do you need artificial heart valve? Well, the valve that I show you in the first slide, where you have these, it's a nice, very nice tissue valve from the native and the mitral valve. They might fail, right? For example, here the aortic valve, for some reason, for sort of disease, which is actually, in many developing countries, for example, rheumatic fever can damage the valve in many kids, many children, which many of my friend actually, when I was a kid, got this rheumatic fever disease. So the valve is damaged, and once the valve is damaged, in this case, for simplicity, we'll take this aortic valve because it's simpler. You need to typically the procedure is to replace this valve, and one of the ways to replace the valve is with this, mechanical valve. And the most popular valve is called bileaflet mechanical heart valve. So you have these two leaflets that can rotate around a hinge that open and close under the pressure of the heart. So this valve is very durable. So it lasts long, very long time, and it's great in terms of durability. However, it has complication because as it is artificial, it is rigid. You could create blood damage. For example, when the valve closed, you could have leakage flow that go back through the tip of the valve or in the hinge, and also we have this high leakage flow can damage red blood cell and activate leaflets and create thrombosis. And that is the big problem that patient need to take a medicine to sort of maintain the condition and avoid this. And so recently, people try to develop different kind of valve. For example, Dr. Dasi, lab here, for example, developed this polymeric valve, and Dr. Karatba here at UCLA developed this tissue valve, and one of these our collaborator is Dr. Sack from Texas Austin developed this tissue engineering valve. And so this area is the area that very active, and we want to contribute to that. So we want to apply our method to investigate the flow through a valve. And so complication here is, for example, this bileaflet valve, you could have thrombosis formation if the valve is not functioning well. You can see that thrombosis can form heavily in the valve, and obviously when the valve cannot be open and closed, blood pressure inside the heart is going to be changed, and that would be pretty bad because the heart should adapt to that pressure and basically lead to pathological condition for the heart very quickly. And the other one is that when you have the tissue valve and trilateral valve, you could which is closer to the native valve, you still have issue because the surface of the valve, because it's not, again, it's artificial. You could have some problem called calcification, where calcium actually deposit on the surface of the valve and make the valve stiffer, and over time it would be difficult to open and close as well. So you have issue both in these bileaflet mechanical heart valve and the tissue cellular valve. So we apply our method for this left ventricle problem, and we implanted virtually this bileaflet valve in the output position. And you see that we are able to capture this jet near the tip of the valve as the valve closed. So first, the valve opened, it created a high-speed jet, and then as the valve closed, it created this leakage jet that go back to this left ventricular chamber. And so we are able to capture that. And that's here the detailed process of the valve open. It create, now look again, we're looking at is vorticity field, which is the way to quantify where the flow become highly deformed, right? The fluid particle was basically highly deformed. And so you see that on the shear layer form on the surface of the valve, and it as the valve open near epistically, and it become turbulent, and again the flow very small structure that you see on the right side here indicate that the flow transition to turbulent in the aortic sinus. That's what you see here. Okay, so we also apply this technology for this trilateral valve, and for the trilateral valve, the dependent of the flow structure, also depending on how this material of the valve, basically the mechanical of the tissue, will dictate how the flow would evolve over time. And that would basically motivate the design of this tissue engineering valve, and where the flow when the tissue with the leaflet are put it into a bioreactor that basically mimic the loading condition of open and close of this valve. This is one of the work that we published 6-7 years ago when the valve was first developed. So okay, so now we talk about this valve, and then we move a little bit of gears to aneurysm, right, which is the part of the brain. So we see that the transition to turbulent, or the complex flow, can appear in the heart, inside the ventricular side and the aortic side. So we see that. But what happened in the brain? And one of the problems that we look at is the brain aneurysm. So what is brain aneurysm? Well, for some reason, for these brain artery distend and create a balloon. And when this balloon bursts, patient can suffer from bleeding, and that would create a very bad consequences for patient. And and most of the cases, aneurysm was diagnosed by accident. So patient come to the hospital for some reason, and then discovered that they have this aneurysm. And one of the actor from this movie Game of Thrones, she got this aneurysm disease. So so the problem is that can you and it is obviously the brain is difficult to operate and difficult to monitor. But the question is, once you have the aneurysm, can you sort of predict how it would grow, how it would rupture, or it would stay the same? That question was the main debate. How can you predict that? It would, today there's still a lot of debate, and it's unclear how you can predict if it's continue to grow until it bursts, or it stabilize and stay there. We actually don't have a clear answer. So we want to contribute to that, because we have the technology that was successfully applied for the heart, and see how now it would be applicable for the brain. Okay, so the first step is to do experiment, and we collaborated with Dr. Lamire groups from Minnesota, and she did an experiment. So she did the volumetric measurement of the so to build this phantom model of this aneurysm, brain aneurysm, and we do this CRV simulation, and we show that actually, interestingly, this vortex ring appears here also in this aneurysm as well. And for example, here, this volumetric measurement will show that a vortex is formed right in this near the neck of this aneurysm. This is from experiment. And in simulation, we'll see the same thing. So we see that this vortex ring is formed in the neck, and also we are able to resolve this, what is called secondary vortex, VC2, inside this aneurysm as well. And our question was, okay, so this complex flow obviously occur, but why is that? What is the reason? And we find out that the reason is that the pulsatility of the flow, which is defined by these delta U, the change in the flow velocity with respect to the mean, is the one that actually control how these vortex phenomena appear. And if you see that in the low PI, so the flow is sort of very stable, you have a shear layer that constantly stay in the neck of this aneurysm. However, if you have a high pulsatility flow, so high PI flow, the flow, the vortex ring actually appear in this case. And if you stop this one, you would see that this one, okay, let me stop this at some point. This one, the vortex ring actually form inside this aneurysm, and we propose a number called aneurysm number that basically correlate to the width of this neck, the neck of aneurysm width divided by the diameter of the artery and multiplied by pulsatility index. This aneurysm, we show that it can predict this flow mode, which is stable flow and what we call unstable or vortex ring mode. And this aneurysm has been studied subsequently by quite a bit of author to correlate with the growth of aneurysm. The result is not clear, but seems like this aneurysm number is useful in predicting the flow mode. Okay, so look at this three-dimensionally. So you, from the flow low PI, you can see this stable structure, but the high PI is, the flow become a vortex ring, an inclined vortex ring, similar to the one that we see in the lab appear in these aneurysms. So now, in conclusion, we see that these vortex ring appear in many places in the cardiovascular system, right? From the heart valve, from the brain, or that whenever you see a pulse, you basically see this vortex ring. And recently, we are working with Sanford Health, which is a local hospital here in North Dakota. We want to apply these principles for patient-specific data to understand if it is appropriate to monitor or to provide some suggestion for the clinician that if an appropriate operation, let's say for example stent implantation, needs to be carried out. So that's what we're doing. And so we take these data from the Sanford Health Hospital. We perform simulation. We analyze the signal signature of the flow, and we compare with different patients, and we perform some fluid analysis called dynamic mode decomposition, basically separating the flow into different modes and see that if we can actually predict this mode that happen in the flow. And that's what we have done in the last year. And we show the importance of how this mode would be useful in monitoring the progress of the disease. Okay, so I have about 10 minutes left, my few minutes left, so I'm gonna show some part of this current work project. So in this part, actually, the this part is carried out by my PhD student, Lashen Kikosh. He is the one actually doing most of the work here. And so as I mentioned earlier, we have a project where we look at the fluid, the role of fluid flow in cancer cell growth, and he is the one who's doing this. And so okay, so I'm gonna go quickly. So he's able to develop this model, and that is, be able to capture the mechanic of the cell membrane and also the cytoplasms. And he is, basically he has a very good way of resolving this membrane structure using dissipative particle dynamics approach, where we can actually capture the interaction of this particle on the surface of the membrane. And here I show an example. So this is the experiment by Mills, and where so we start with a very simple cell. It's actually the simplest cell, which is the red blood cell, because this red blood cell has been studied for a long time, and that have a lot of data, and that's why we started with that. And this is a very famous experiment from Mills, where they have these they capture this red blood cell by optical tweezers, and then we apply these microbeads to this RBC, and then they pull it under different load. So at the tip, and that from for example from 0 to about 200 piconewton, the cell will basically stretch. And Lashen actually performed the simulation, using DPD, dissipative particle dynamics code, that he would be able to replicate the process of this deformation, and he showed that with a very limited number of elements, which is important when you want to resolve the cell dynamic with a large number of cells, then you'd be able to capture very good experimental data. For example, the black dot here are the experimental data, and the blue one are the simulation result, and we capture this deformation of the cell with a good agreement. So here, for example, to illustrate the process, so we are able to capture the cell deformation in that way, and we are able to simulate this cytoplasm fluid inside the cell, during this process. So Okay. Okay, let me see. So, okay, I accelerated that a little bit. You can see how this fluid would affect this cell motion. Okay, now we are actually we put the cell into microversal to see how the cell behave under the flow condition with our method, and we found that the response of this the cell to flow we actually is very similar to what is observed in experiment, which is what is called parachuting. So the cell, the RBC is here, and it become it's kind of cone shape as the impact of the flow in a microchannel. And so, okay, let me put it here. So this process should look like this. So you have this cell, so it's deformed into a parachute shape and propagating along the channel. So I have about okay, so about two minutes. So I'm going to be go to the conclusion. So okay, so our effort is now we are very confident about our model for the cell, and we are working in a project that looking at the interaction of this RBC with the next step, which is the focus of our project is interaction between RBC and other type of cell, for example, prostate cancer and breast cancer cell, especially migrating to bones, and that is our current focus. So I will stop here, and so that is the the scope of work that we have done. So we work with cardiovascular flow from very large scale blood flow in the heart and brain, and going down to cellular flow, which to this RBC scale, and I hope that this information would be useful for student in the department or anyone who is interested in the area. And yeah, so I stop here, and if you have any question, would just let me know, and I'm very happy to answer.
Well, thank you, Trung. Yeah, this is an interesting talk. So I encourage anybody who has questions to raise them, but I know I have a few. So while we wait for the questions to come, I'm just going to ask my questions. Yeah, Trung?
Oh, yeah, please go ahead.
The first thing is I'm quite intrigued with what you talk about is the intracellular fluid flow when you model those deformations and mechanical stresses in this blood. And not just for cancer cells, right? Obviously, the survival of the cancer cells, depends a lot on the flow it experiences as it metastasizes. But I was just wondering, even in the scenarios where you have platelets being activated with high shear flows in, mechanical assistive flow devices like blood pumps, where you get a lot of clotting, a lot of platelet activations, a lot of neutrophil activations and clotting, all this bad stuff, right? And it all depends on the stresses that the cells experience. Would that just depend on the extracellular fluid and cell interaction, or does it also depend on maybe the flow within the cell and kind of exchange that intracellular fluid mechanics may experience, leading to the adverse effects? And would your tools that you develop be suitable to maybe investigate some of those?
Yeah, thank you, Yap, for your question. I think it's very actually a very interesting question, and I think there's in the literature there are several groups has looked into that problem. So the difference between viscosity of the for the cytoplasma and the outer fluid, which is the blood. I mean the plasma of the blood. So yes, so there's a impact of the fluid characteristic, specifically viscosity of the cytoplasm. Yes, definitely, that affect the deformation of the cell and how it would how the membrane would be stretched. Yes.
Mm-hmm. And I'm thinking that even just the not just the membrane itself, but in the inside of the cell, if you have specific fluid mechanics, maybe that would be bad for it. Then maybe that's why platelets get activated that much, or neutrophils get activated that much, and leading to neptosis and all the interesting cellular cellular mechanobiological responses that leads to clotting And Neil, I thought your tools would be really nice, to maybe start investigating that. The other question I have is on to ask your opinion on what is the state of the art in terms of the aneurysms. So for the longest time, I've heard a lot of people are very interested in aneurysms, fluid mechanics, because they believe that the mechanical patterns and stresses within the aneurysm can be used to predict whether the aneurysm grow or it regress or is stable or is not, and whether the aneurysm eventually breaks. So they believe that mechanically, the mechanical environment is predictive of what's going to happen to this patient. What is your view, in terms of that direction of investigation?
Yeah, so I thank you for your question. I think that's the story always, in this field, bioengineering field. This question is always complicated because mechanical is an important stimuli, but it's not all, right? I mean, it's an important part, but as we see in our work, it's just one important. There's many other things that we actually has not been known yet. So this, yes, is a lot of debate around that. Um, um, uh, is that all? Is that if you can resolve the flow, is all? Well, the thing is that the tissue wall of aneurysm actually changes with time. For example, at first stage when the aneurysm is small, the wall is lined with endothelial cell, right? Mostly they found that, but at larger, or in some cases, or in the later stage, the wall actually is mostly collagen, so there's no it's no EC anymore. And so the idea or the opinion is that the mechanical force that impact on the wall and in fact the growth of EC cell probably it might be less relevant in that cases where you have in certain aneurysm. So it's unclear to me, and so I would say that it might correlate to some point, but it's a nonlinear process. It should, it's not, it's a one dimension of the problem. It's not all dimension. So I would say the first step is to understand. So we have to be clear now. Very close. I mean, we have been debating for a long time, but recently in the last 3 years, we come to the conclusion that high frequency fluctuation in aneurysm is real, right? So in the past, people would say, okay, blood flow in the brain is laminar. There's nothing called fluctuation. There's called vortex formation. There's nothing called transition to turbulent. But no, in the last 3 years, people, different group, in the last 10 years, a lot of work, including our work, showing that no, high frequency fluctuation is real. This transition to turbulent is real. So this is the first step, I would say, the first step showing that this transition phenomena actually is real. So how we link that to the biology, it would be, I think, is the next step. How we will signal, mechanical signal transition to biological signal would be the next step, which I have no answer yet, but I hope that would be the next, the next question.
Okay, yeah, we got a couple of questions. Sorry, I missed that. I didn't click on that button. So Sam asks, firstly, thanks you for the interesting talk. And then he says, oh, actually, sorry. Okay, so I'm going to just read the question for you, if that's fine. And he says, how do you plot the vortex strings in 3D, lambda 2 criterion? I think so, right? That's what you did.
Yeah, so I think it actually depends on the purpose. For example, in the experiment with with vortex string in the lab, we use vorticity magnitude because we want to use the same way as the experiment, right? The experiment plotted that with vorticity magnitude, so we plot that with vorticity magnitude. So depending on the situation, but yes, vorticity magnitude or lambda 2, yes.
Chris Rollins is asking on the implications of the vortex rings simulations for things like stent design. Do we need to modify mechanical interventions like this to control unwanted forces on the blood vessels, and how would you model that effect?
Okay, that's very interesting question. Yes, so actually we show in our preliminary data is that this vortex ring actually appear, especially in aneurysm, right? People put stent while they have different fancy name, but basically the stent. and there in brain aneurysm, and this vortex ring form, and that ring actually impact on this mesh on the stand, and that create, you know, very locally high shear. Okay, and so there's a different group actually looking at this, how to actually improve the cell, and one of the way, which is pretty much straightforward, that is not really I'm not sure, is challenging in practice, which is coating the cell with endothelial cell, coating the mesh, coating this stand with EC, which they did. They demonstrated it's possible and would accelerate the healing. You know, make the flow, basically block off the flow going to the aneurysm, and then basically over time you're gonna have thrombus formation, and over time, you know, the aneurysm will basically disappear. That was the idea. Yes. So in that sense, design of the stand would be you know, the side, a mesh side, and how you coat the surface would be considering that you have a very local structure of the flow that impacts on the mesh. Yes.
Mm-hmm. All right. Is there any other questions? Right. Otherwise, I think then we'll just, if you join me to thank the speaker once more. And then it's really been a pleasure, Trung. It was refreshing to see what's going on the other side of the Atlantic, you know, in terms of wonderful new techniques and vorticity, pretty pictures. So those, you know, and also their implications on the biology and physiology. So it's really been a pleasure to have you here. Thank you for your time. And we look forward to the next time, maybe when you can actually visit us in person.
Yeah, thank you very much, Dr. Yap, and it's my pleasure and my honor to be here in the seminar, and I hope that I have a, you know, future opportunity to share my work with you. Thank you very much.
Great, thanks, guys.
Yeah, bye-bye.
Thanks everyone for attending.